And then they come and show you some data which agrees or doesn't agree with those predictions. And my feeling is that it's useful to know a little bit about the data beforehand, to see the landscape, so you know what it is that these theories are trying to predict, rather than have a theory predict something and show you a kind of random piece of data that fits it. So I'm going to give an introduction to what nuclei look like. I don't mean look like, but I mean what their spectra look like, and a little bit about their structure, and then introduce some simple models. Most of this will be tomorrow, and this will mostly be today, but we'll see how it goes, okay? And remember, I encourage questions. So this is an overview that applies not only to nuclear physics, but to many areas of modern science. There are two ways of looking at many-body systems. One is a microscopic approach, where you look at the individual constituents and their interactions. And in nuclei, that means what is the force that binds nuclei, and why do nuclei do what they do, okay? This is actually the subject matter of most of the Talent courses so far, and it's a very important approach. A complementary approach is a macroscopic one. This should be femtoscopic, I guess. A macroscopic one where we look at the many-body system as a whole. We look at the nucleus as a whole with a shape, with vibrations, rotations, and excitations, and we try to assign quantum numbers and predictions for the system as a whole. And these nuclei exhibit remarkably simple patterns. We try to understand what those patterns are and what is their origin, okay? So this is more a question of what nuclei do, and this is more a question of why nuclei do, but those labels are a little bit fuzzy because both sides do both. Okay, so these are the two perspectives you can use to look at nuclei. I will focus mostly on this, but you will get plenty of this as well during the course. Okay? This is the plan for today and tomorrow. I want to talk about three key ingredients for understanding nuclei. These are very simple ingredients. I want to give a brief introduction to a couple of idealized models. Now this brief introduction will be like one slide for each. And the only reason for that is to give you the names, a few pieces of jargon, so that when I discuss the data, the empirical behavior of nuclei, I can attach some labels to that behavior. But I won't go in any detail here about these models. Instead, I will come back to them after I've shown you the data, and then go into those models in some detail. Okay, key concepts. These are the three key ingredients for understanding nuclei. Now, it's not everything, but this gives you a good start. One is that the nuclear force is short range and attractive. That is, nucleons, protons, and neutrons interact with each other when they're close to each other. That's a very hand-waving way of saying it, but it has the basic idea behind it. The Pauli principle is the second, which has two aspects. It controls the occupation of these nucleons in specific orbits, and it implies anti-symmetrization of the wave functions, and that has a big impact on residual interactions, and as you will see, is the reason basically why even nuclei have 0+ ground states. And then two-state mixing, or mixing in general. When we do a calculation of any aspect of nuclear structure, we start with some set of basis states. And we have a Hamiltonian. That Hamiltonian invariably mixes those basis states. And what comes out is a result of that mixing. It's the origin of collectivity, coherence in the wave functions. And the simplest one is two-state mixing. And I'm going to go in some great detail on two-state mixing because it's the basis for multi-state mixing. And in fact, very often if you do a multi-state mixing calculation, you can decompose it into approximately a sequence of two-state calculations. And so I'll go through some formalism for this. And this afternoon there'll be some exercises on this. Okay. So I said that the nuclear force is short range and attractive. How do we know that? Well, there's a lot of data that tells us that. But one piece of data is nuclear masses, which very simply give a clue to the range of the nucleon force. You will see this slide 3 times today and tomorrow with different aspects of what these masses tell us. But the total binding energy, or total mass of the nucleus, is the sum of all the interactions of all the nucleons in the nucleus. Mass differences are differences of masses between neighboring nuclei. Those are the same as separation energies. They can give evidence about shell structure, phase transitions. We'll come to that later, and this will also come to later. Now, if you talk about the total mass of a nucleus, each proton and neutron has a mass of approximately a GeV. That means a typical heavy nucleus has a mass of 150, 200 GeV. And excitation energies in even nuclei are on the order of an MeV. So it's pretty hard to learn much about that by looking at the total mass. One always looks at some function of the mass. And one is the binding energy, that is the sum of the energy required to remove each of the nucleons to infinity, and often the binding energy divided by the number of nucleons, the average binding energy per nucleon. So I want to look at that and show you a very simple plot that we'll see that this immediately tells us that the nuclear force is short range. So this is about the simplest data you can imagine. It's a plot you've all seen. It's in almost every textbook. It shows the binding energy of a nucleus per nucleon divided by the number of nucleons. And it starts off, and the scale here is MeV, and this is 0, and that's 10 MeV. And so it starts off and it increases here, and then somewhere around in the region from oxygen to cadmium, it kind of flattens out. And basically, in first order, it's flat after that. There's a small drop, but we can approximate this as something going up and then flat. And I want to try to understand that and understand what it tells us. Okay? So I want to look at the simplest possible model you could imagine, which is clearly wrong. I like to look at wrong models because they often contain some essence of the real situation. So I'm going to assume that every nucleon interacts with n others, and we will look at different values for n. And all those interactions are equal. And you know that's not right, but we'll do it anyway. And we're going to look at the resulting binding as a function of n and mass. And we'll compare with this binding energy for a plot. Okay, so this is complicated looking, but it's actually very simple. A column is for the case of each nucleon interacting with a certain number of others. So this column corresponds to each nucleon interacting with 2 others. And I do that for a case of total nucleons 3, 4, 5, 6, and 8. Okay, I don't know what happened to 7, but okay. So if you have 3 nucleons and they interact with 2 others, this one will interact with this and this one with this and this, and this one with this and this. Total of 3 interactions. And if I now divide by the number of nucleons, I get the number of interactions per nucleon is 1. If I go to 4 nucleons, each one interacts with 2 others, I have a total of 4 interactions. So the number of interactions per nucleon is 1. 5, I get 1, 1, 1, 1, 1. So if this were the case in nuclei, the binding energy per nucleon would just simply be 1. It would be this line here. So this is what you would get for the binding energy per nucleon if each nucleon interacted with only 2 others. Suppose each nucleon interacts with 3 others. Well, here there aren't 3 others to interact with, so that's the same. Here, this nucleon will interact with this one, and this one. And similarly, you count the number of interactions, 1, 2, 3, 4, 5, 6. There's 6 interactions, 4 nucleons. So the total number of interactions per nucleon is 1.5. If I go to the next one, you can do it, you can work it out yourself. It's 1.4, then 1.5, then 1.5. If I plot those as a function of A, I get a line that comes up like this and then goes off constant, approximately constant at 1.5. If I go to 5 interactions per nucleon, I'm not going to do the counting and things like this, but here it's obviously 1 by definition because there are only 2 others. Here it's 1.5 because there are only 3 others. Here, if you count the number of interactions, you get 2 interactions per nucleon. The binding energy per nucleon is 2. here it's 2.5, here it's 2.5. And so you would get a curve that would go up like this and then be flat. And I wonder now whether I have a mistake here with 8 and 7, but it doesn't matter, you get the idea. If each nucleon can interact with all others, then every nucleon interacts with A minus 1 others, and they're A nucleons, so you have A times A minus 1 over 2 interactions. And if you divide by A, the number of interactions per nucleon, you get A minus 1 over 2, which is this line here. Okay, so you can already see from this very trivial way of looking at it that you have a curve, this curve here, where each nucleon interacts with all the others, doesn't look like this plot. It does look like the beginning of the plot. This curve where the binding energy per nucleon is constant doesn't look like this plot, but it does look like this part. Okay? And so what you see is that you can get a curve that resembles the data if you assume that each nucleon interacts with 8 or 10 others. Then the binding energy per nucleon would go up and then become flat. And so from this very simple counting scheme, which is hugely oversimplified, you can conclude that each nucleon interacts with 10 or so others. 10 could be 5, it could be 20, but that ballpark. Which means that the nuclear force is short range, and it's shorter in range than the size of heavy nuclei. Okay? So from the just measuring the masses of nuclei, putting them on a scale basically, we can already tell that the nuclear force is short range. And it's obviously attractive or we wouldn't be around to ask the question. Okay, now two-state mixing. There's going to be some heavy formulas here. You will have these slides, so I won't go through every detail of the derivations. And anyway, you've probably all seen this. I want to present it in a slightly different way, which gives you some universal functions. Okay, so here's the problem we want to solve. I have two levels called E1 and E2 with Arabic subscripts, and they have an unperturbed energy spacing delta E unperturbed. They have unperturbed wave functions phi 1 and phi 2. Okay, now I assume that they interact with some interaction V. Okay, and what happens? You know that levels that interact repel each other, and so they will be further apart after mixing than before. And the amount they push each other apart I define as delta ES, S stands for shift. And the final energies are given by E1 with a Roman subscript and E2, and the final wave functions by psi, psi 1 and psi 2. Okay, I want to define the quantity because this is really the key to everything. R, which is the unperturbed energy spacing divided by the interaction. And you will see that everything can be written in terms of R. So you all know the solution to this. I mean, this is really elementary. That the final two energies are given by 1/2 the sum of the initial energies plus or minus 1/2 the square root of the difference in those initial energies squared plus 4 times the matrix element squared. And I can take out, the E2 minus E1 is the unperturbed energy difference. So I can pull that out and I get, this is the same, I get plus or minus delta E unperturbed over 2, 1 minus 4v squared over delta E mu squared. All I've done is just take this out of the square root out here and call it delta E mu. And now using R, I can write this as same thing. This is the same square root of 1 plus 4 over R squared. Okay? The perturbed energy separation, that is E2 minus E1, is then given by, so I'm just going to take this and take the difference E2 minus E1 using the plus sign in one case and the minus sign in another. I get that it's the unperturbed energy separation times the square root of 1 plus 4 over R squared. And now if I write the perturbed energy difference in units of the initial one, is this getting faint already? Okay. If I write the perturbed energy difference in units of the unperturbed, I get this, that the perturbed energy separation in units of the unperturbed is just the square root of 1 over 4R squared. Okay. you can go through the rest of this if you want. So this is a universal expression for the final energies in units of the initial energies, and it only depends on this one quantity r squared. Okay, and it doesn't matter whether the initial levels are separated by 3 electron volts or 22 GeV, or whether the interaction is a kilovolt or an MeV. You can always write it in terms of R. The only case where this doesn't work is if the two initial levels are degenerate, because then you have 1 over 0 there and you have to use this equation, but other than that it works universally. The mixed wave functions, psi 1 is going to be a linear combination of the two unperturbed wave functions with coefficients alpha and beta. Psi 2 will be the orthogonal mixture, minus beta phi 1 plus alpha phi 2. I have to have alpha squared plus beta squared equals 1. And this smaller amplitude beta is given also in terms of R by this expression. Okay? And now you can make universal plots. This shows beta, the amplitude of the smaller, as a function of R. And remember, R is the unperturbed spacing over the matrix element. So if the unperturbed spacing is large compared to the matrix element, you're over in this section. I'm having trouble with this. You're over.
Yeah, fading stuff.
Okay, so I'll do that. You have the curve is here, corresponding to small beta, so the mixing amplitudes are very small. If the matrix element is comparable to the unperturbed spacing, that R would be 1, you're down here, you have a very large mixing amplitude of 0.5. The largest you can have is 0.707. This shows the repulsion of the admixed states, so it's the repulsion, the shift in units of the unperturbed separation, and there are two curves on here just because to blow that up. The upper curve goes with the lower scale, and the lower curve goes with the upper, and so you can just read off this plot for any case you want what the final energies are, what the repulsion is, and since you know the initial levels, you can get the final levels. So this gives you a universal way of getting the final energies for any set of initial energies and matrix element. Okay, clear? Here's a table with some examples. These equations refer to equations in my textbook. Don't worry about that. So here are examples of cases for R, ranging from very almost degenerate levels to levels that are far apart. This is the shift in energy compared to the unperturbed energy. So if they're very close to each other compared to the matrix element, the shift is big. If they're very far apart, the shift is very small. If they're very close together compared to the matrix element, the mixing amplitude is large, and it goes down. Okay? Here I do a specific case where I take 100 kilovolts unperturbed energy separation, and then these R values correspond to these interaction matrix elements. If I have an unperturbed spacing of 100 kilovolts and R is 0.2, it means the matrix element is 500 kilovolts, 100 over 500. And in that case, the shift in energy will be 452 kilovolts. So these levels that are 100 kilovolts apart initially will each move by 452 kilovolts. That's a huge mixing. If I take R1, the wave function amplitude will be 0.53, and the levels will each move 62 kilovolts. If I take an R of 10, the wave function amplitude is 0.1, and each level will move 1 kilovolt. Okay, and you can fill in any other numbers you want here. This gives some nice examples. Okie dokie. All right. Here is a concrete example, which I don't think I'll go through, but it'll be in the slides. I take a case of two levels which are 200 kilovolts apart with a 50 kilovolt matrix element. So that's an R of 4, and that's in between 3 and 5, so you can already guess. Well, you can actually look at this and guess what beta is going to be. It's going to be somewhere between 0.19 and 0.29, and it works out to be 0.23. And the shift is going to be in between, where is it? The shift will be between 0.04 and 0.1, and it turns out to be 0.059. You can work through this, okay? It's just designed to give you a concrete example where you can actually work it out, okay?
Excuse me.
Yes.
I have a question. That previous slide. This in the case of R equal 0.2 or 0.5, that is very large. Shift is very large.
The shift is very large compared to
Yes.
yeah.
Compared to the
This is a case where the matrix element mixing the states is larger than their separation,
yes.
and they go,
Yes.
okay?
In this case, can we describe this case by perturbation theory?
Well, this is an exact answer because it's just two-state mixing.
Yes.
So this is exact.
Exactly. Not perturbation.
No.
No, I think he has a problem because these formula are derived using perturbation theory,
Yes.
and in
Yeah.
this case, obviously, the interaction is maybe comparable to the
Matrix.
Hamiltonian, the
Yeah,
matrix element Hamiltonian is compared to the interaction.
If you diagonalize the matrix, you get this.
Mhm. Yeah, I think that this was here for even though I don't know what to say
Okay.
here.
I want to look at two specific cases. One is degenerate levels. This will turn out to be very important. For degenerate levels, delta E unperturbed is 0, and so R is 0. You can't use the formulas with an R in the denominator, but you go back to the original ones, and you find out that the final energies are the unperturbed energy plus or minus V. That means the final levels are separated by 2 times the matrix element. So they are 2V. And that has a very interesting implication, which is sometimes very useful. 2 levels that mix can never be closer than twice the matrix element. Okay? And in fact, this historically was very important in the study of odd mass nuclei, where the Coriolis interaction is important. There were levels that were found that were isolated 2-state systems that mixed, and they were closer than twice the matrix element. And so that led people to understand you had to attenuate the Coriolis mixing. But it has lots of other implications. In this case also, the wave functions are as mixed as they can possibly be because the initial separation is 0, and so beta is just 1 over the square root of 2.707. Okay? Another case which is very useful is weak mixing. That corresponds to R much greater than 1. And if you plug in the formulas, I'm not going to go through this, it's just algebra, you get that beta is 1 over R. Okay? So beta then is simply the matrix element divided by the unperturbed spacing. Okay? And the energy shift is the unperturbed energy shift divided by R squared. Okay? I'll do a couple of examples.
So this is perturbation theory.
This, yes. So suppose you take R of 10. Okay? These are approximate formulas. Suppose you take R of 10, then this formula would give beta of 0.1, and it would give a separation of 0.01. The exact results, yes, thanks for saying that. The exact results are beta equals 0.0985 instead of 0.1, and this quantity 0.0099 instead of 0.01. So R of 10, these formulas are essentially perfect. Even for R as small as 3, this is where the initial separation is 3 times the matrix element. That corresponds to pretty big mixing. These approximations give you beta of 1 over 3 of 0.33, and the energy is 1 over R squared, 1 over 9, which is 0.11, and the exact values are 0.29 and 0.101. So even for quite large mixing of 0.33 amplitude, these formulas are pretty good. Okay, and so these are very, very useful guidelines to always keep in your mind when you're looking at nuclear levels and their mixing. Now, real nuclei have more than 2 levels, and they mix. What time is it? Oh, we got plenty of time. Okay. And they often mix with each other, and so then you're typically solving a matrix like this, which you have to diagonalize, And the final wave function will be, just like before, it'll be a sum of amplitudes of all the initial wave functions with different amplitudes. The details will depend on the interactions and on the energies. I want to discuss one important case where all of these levels are degenerate. Now that's not a realistic case, but it contains the essence of a lot of physics we'll discuss. And so I want to, this is what I would call an extreme toy model. If you apply it in a realistic case, you would get answers, like for samarium, you would get answers like 10 to the 14th, whereas the real answer is 200, so it's approximate. But, but it contains the essence of the physics. So suppose I take n degenerate levels, and suppose each one mixes with all the others equally. So if I have 5 levels, this one would mix with this by interaction V, this with this by V, this with this by V, and so on. They would all mix by matrix element V. What happens? What happens is this. 4 of them go up by an amount V, and of course you have to conserve the total energy. So one of them comes down by n minus 1 V. Okay? This, and the wave function for this level, is all equal amplitudes of all of these basis states just with a normalization factor. This is the essence of collectivity in nuclei. You have a set of states which mix, one state comes down, its wave function is all in phase, and it has the collectivity of the whole system in it. Okay? And you will see this again and again and again. And thinking about this will instantly, as you'll see, help you understand the entire evolution of structure across the nuclear chart. So that's what I just said, absolutely fundamental result, foundation of collectivity. Coherence, collectivity, and the energy lowering all grow with n, goes down as n minus 1, so the more states you have interacting, the lower the collective state will be. And as I said, this largely explains a lot of the general features of the evolution of structure. I want to apply this to a calculation of a transition rate. So let's assume I have n degenerate levels. Okay, we know what the wave function will be. It will be this, where a, this normalization factor, is 1 over the square root of n. And I want to calculate, let's assume there's a ground state which is not mixed, and these are 2+ states. I want to calculate the transition rate from the final 2+ state to this ground state. I'm not sure all of you know this notation. All right, does everybody know what a BE2 is? Anybody not know what a BE2 is? It's no embarrassment. Okay. So a BE2 is the notation we use for the square of a transition matrix element. It's related to the transition rate, but there's some other factors that go into the transition rate or the lifetime. But it's defined as 1 over 2 times the initial spin plus 1 times the square of this reduced matrix element from 2+ to 0+. Okay? I'm going to calculate without the square first. So the matrix element itself, from this 2+ to this, is going to be the matrix element to the 0+ with this mixed wave function there. And so I can write that, since this mixed wave function has this simple form, it's just simply A times the sum over all the individual matrix elements. Is that clear? And now I'm going to make the approximation that all these individual ones are equal. That is, the matrix element for each of these initial unperturbed states to the 0+ is the same. And I'm going to call that, I think I call it, yeah, okay. I call it W. I don't know why I call it W. Okay, so now I take this, each one of these individual ones is W, and so I get that the matrix element is N, because there are N components here, A, W, N, A, W, and when I put in the value for A, 1 over the square root of N, I get that this is the square root of N times W. The BE2 is the square of this. I guess I've dropped a factor of 5, but it doesn't matter. So the BE2 is proportional to N W squared. So that says that the transition rate from this final mixed state is N times the transition rate from any one of these. Okay, or I shouldn't say transition rate, I should say the BE2. So that's an enhancement of n. If n is 5, that's an enhancement of 5. If n is 10 to the 12th, that's an enhancement of 10 to the 12th. And you will see that this is a gross approximation. Gross doesn't begin to describe how gross it is. But the idea that the collectivity of these transitions increases with the number of states that you have to start with persists. Okay. Okay. It's a fundamental property of collective states. Okay, so that's a kind of quick introduction to two-state mixing, and now I want to start to look at some of the data. I want to look at nuclear level schemes, how they change with proton and neutron number, what the challenges for theory are, and especially what are the key observables for testing theories. And I'm going to discuss later on, mostly tomorrow, some geometrical models in some detail, and today I will discuss the independent particle model as well. My discussion of the independent particle model will be very simple, and I don't want to say hand-waving, because I use the word hand-waving to mean what you say if you don't know the answer, but it will be, let's say, extremely simplified. Pete, later in the week, will give a much more formal presentation of the independent particle model, and also we'll both talk about residual interactions. First, to try to describe the data without any understanding of the physics of what's going on is very difficult. So I want to bring in a couple of slides on basic models without deriving them or anything, just sort of like a deus ex machina pulling it out of the sky, just to give you some labels, okay? Okay, first of all, what observables will we look at? When you study nuclei, you have to measure something. There are a lot of things you can measure. These are not all of them by any means, but they're the ones that I will talk about most. Masses are one thing, and we will find that we can learn a lot about nuclei from their masses. We already learned that the nuclear force is short range and attractive. We will find out later on we can go much, much further. Nuclei all nuclei have a ground state, which is good. They have excited states, and these are it's not a real nucleus, it's just a random example. Almost always, I'm talking about even nuclei. I will discuss, in the third week, I'll discuss odd mass nuclei. Almost always, I would say 99% of the time, the first excited state is 2+, and probably about 97% of the time, the second excited state is 4+, and then you have other states. Okay? So we will look at these states, their spin imparities and their energies. One important measure of structure, which does not tell you everything, but it's a good first guide, is this quantity R42, which is the ratio of the 4+ energy over the 2+ energy. So in this case, it's 2.5. Okay? I stress that whenever I look at an even nucleus and ask myself what's going on, that's the first quantity I look at. But it's very important to understand it doesn't tell you everything. Okay. Very important also are BE2 values, basically transition rates from these various states. Okay. Typical notation is the thicker the arrow, the bigger the BE2 value. That's a common practice. Okay, so these are the observables, most of the observables we'll look at. Okay, now the idealized models. They're basically two classes. There's the independent particle model, which is just a model of nucleons running around the nucleus in orbits. And that's the foundation of sort of nucleon-based picture of the nucleus, the shell model, if you want. And I will go into some detail on that. And then there are collective models, where this model becomes impractical. You resort to collective models. Remember the very first slide I talked about a microscopic and macroscopic approach, one looking at nucleons and their interactions. This is the simplest version of that, I mean utterly simple. And then I talked about a macroscopic picture where you look at what the many-body system as a whole is doing with its own quantum numbers. That's collective models. And I'm going to talk about two collective models right now, very, very briefly. A harmonic vibrator, and what you should picture in your mind there is a spherical nucleus that can vibrate. Okay, and that's all I'm going to say about it basically for now. The other simple model is a deformed rotor. What I mean by that is a nucleus that's shaped like, and I'm sorry to have to get patriotic about this, like an American football. All of you know what an American football looks like? Anybody not? Okay, so looks roughly like an American football. And since it's non-spherical, it can rotate. It can also vibrate, and so you get both of those kinds of excitations superimposed on top of each other. These two are collective models. They involve things going on in the nucleus as a whole, and this is a nucleon-based depiction. Okay, so some spherical nuclei are quite rigid, but many of them are soft. Soft means that they can oscillate a little bit. Later we'll talk about this in terms of a potential, where you have a potential that the nucleus can oscillate back and forth, but right now I want to be very qualitative. They can be soft to vibrational motions. The lowest such excitation is a quadrupole excitation, so that's an excitation where you take a sphere and then it looks a little bit like the American football this way, and then looks like it this way, and it goes back and forth. That has 2 units of angular momentum, and so the first excited state will be a 2+ state. Now, there's no reason why you can't have 2 of these excitations superimposed on each other, and so if you superpose 2 of these quadrupole spin 2 excitations, which can be called phonons, you get a 4+ state, and since you're just superposing 2 of the same thing, the energy of the 4+ state is twice the energy of the 2+ state. And that's a 2-phonon state. There are others 2-phonon states which we'll talk about, but for now, just look at this, and clearly R42 is 2.0. So, just bear this in mind. I will use this kind of language to talk about some of the nuclei we'll see. Okay. The other is, nuclei are 3-dimensional. That means they can rotate. And rotational energies in nucleus. So I'm picturing now, just to make it very clear in case some of you are confused, here I have a roughly an American football shaped nucleus. It's not exactly. By rotation, I do not mean this. I mean this. Okay, a quantum mechanical object can't rotate about a symmetry axis. So it's a rotation like this or like this. And I got to orient this back to right? Okay. Those energies follow the energies for the quantum mechanical symmetric top, which means that the energies of these rotational states go as h² squared over 2 times the moment of inertia times j plus 1. Comment here that I should have made before. I use the letter small j to mean the angular momentum of a nucleon, and large j to mean the angular momentum of the nucleus. Okay, sometimes in the literature you will see a large I. Typically, but not always, people who use large I are or have been interested in high spin states, and those who use J tend to have been interested in low spin states. That's not a rule, but it's common. And now I want to use this simple formula and just get one result very quickly. Suppose I put angular momentum 0 in here. Can anyone tell me what this is equal to? There's a hint here. Everybody see that?
Yeah.
Okay, suppose I put angular momentum 2. Well, it's going to be proportional. I don't care about that. 2 times 3. Can anyone do that without a calculator? No? Somebody want to tell me? 6, good. And now a little more complicated, 4 times 5. What?
20.
I thought you said 7. 20, okay. So the 2 plus should be in an
Order of
energy.
magnitude, right?
Sorry? What?
It's of the order of magnitude 7.
Yeah, okay. We'll see later that those differences tell us something. Okay. So the 2 plus state will be at an energy proportional to 6, and the 4 plus 20. Now it gets a little tougher. The 4 to 2 energy ratio is 20 over 6. Can anybody guess what that could be? Okay, 3.33. All right, so that's a very simple result for a rotational excitation. And here's one example. There's this formula again. This is nobelium-254, and here you see this rotational band. And what I do here, you'll see this more later, I normalize this 2 plus, this is the formula. I normalize this 2 plus to this energy. In other words, I use this excitation energy to establish what h bar squared over 2I was. And then I calculated these levels. And you'll see they agree very, very well with the data. You'll also see that they disagree slightly. This 8 plus is a little higher. We'll understand that very soon. Okie dokie? All right. So that's, well, this isn't really anything. Okay, so now I want to look at the empirical evolution of structure. And this is a good place to stop. So let's have a coffee break. Be back here at 11, and we'll look at what real nuclei are doing. But I'm going to assume that you don't know about them, and shell structure, and then two-particle spectrum. That doesn't mean the deuteron, it means something else. And then the emergence of collective features. And I will use these two little models that we talked about very qualitatively, just as a framework to give you some labels. This isn't working. So how do you have to use this? Unless you know how to make it work. Fine? Okay, I'll use this. Okay, so you've seen this slide already. I want to talk now about separation energies. And separation energies will tell us something about shell structure. These are effects on the order of an MeV. They'll tell us about shape changes, effects on the order of 100 kilovolts, and also collective effects on the order of 100 kilovolts. So, you're a theorist. There are two kinds of theorists, by the way. Those who were so brilliant that they became theorists, and those that nobody would let anywhere near a piece of equipment. No, I'm not saying, I'm not specifying. Okay, I'll live with it. Okay, so, all right, so I want to look at these separation energies, and I have a very technical drawing of what I mean by a separation energy. I'm going to look at two nucleon separation energies, the energy required to remove two nucleons to infinity. Here you see a typical nucleus. And this is my rigorous idea of a two-neutron separation energy. Okay? I have to go there. Okay, this shows the data on two nucleon separation energies from mass about 100 and something up to lead, so about a third of the nuclear chart. And you see some obvious patterns, and I want to highlight a few of them. The most obvious thing you see is these huge drops, and they occur at nucleon numbers just after 82, just after 126, and some of you will recognize those as magic numbers, but for now just notice the effect. The other thing you see are these strange flattenings. You'll notice the general trend is down, almost linear. And so if you think about this, instead of coming down in these regions, suddenly the separation energy grows relative to what it would have been. In other words, the nuclei are gaining extra binding, and they're doing that, in fact, by changing from spherical to deformed. But this is what I want to point out for the most part now. These sudden drops at certain special numbers of neutrons, and you can do the same thing with protons. Okay, that's masses. Now I want to look at what I call spectroscopic observables. That means energy levels, transition rates. And the simplest...
Just one question.
Yeah.
Why do, like, almost all textbook people prefer giving the double separation energy, the two nucleon separation energy, rather than the single?
You can see a lot of examples of single nucleon separation energies.
Okay, why do you?
the single nucleon separation energies have oscillations, odd even oscillations,
You don't like that.
which is, well, it's not that I don't like it, it's a pairing effect.
Yeah.
It just confuses the picture a little. But,
also
so I
it
just
gives
do it.
also some data about it.
Single nucleon separation energies are very valuable, we use them all the time. But to illustrate this drop at certain special numbers of nucleons, the 2 nucleon just shows it.
Just the picture is a little bit more beautiful.
Yeah.
Okay.
Okay, so here I want to talk about 2+ energies. That's almost always the first excited state. And you see a pattern here. Don't worry about the red. This originally was used for something else. What you see are sudden spikes at certain numbers of neutrons. Okay, and then in between very low values. And here I take the region around here and just expand it so you can see what it looks like. It's very beautiful. You have this sudden spike here and then a fall off on both sides. Oh, I keep forgetting to do this. Okay, so there's some obvious features. One is high values at certain numbers of nucleons, and if I showed you the entire chart, you'd see that those high values occur at 2, 8, 20, 50, 82, and 126. And if you think about an excitation, somehow it involves moving nucleons from one orbit to another. We haven't talked about orbits yet, but you know they go in orbits. And so this means the nucleus is quite rigid, okay, to moving those nucleons. And so we will see later these correspond to inert cores, to magic nuclei. The sharp drops thereafter are the emergence of collectivity. If you remember, I showed this figure, this toy model where you have a number of states and they mix and one state comes down as a basic feature of collectivity. That's basically what you're seeing here. That n-degenerate level toy model is basically the physics behind this drop. What happened? Oh, I keep forgetting. Okay, this just shows the same thing for protons. I won't go into detail, but you see these same numbers appear. Sometimes other numbers appear, and sometimes they come and go. Okay, that's energy levels. I want to look at transition rates. These are BE2 values. We've already talked about those. Those are from the 0+ to the 2+, or 2+ to 0+, and they represent the square of a matrix element, transition matrix element. And this is what they look like experimentally as a function of neutron number. And you see very characteristic features. Low values at those same numbers of nucleons that we saw before, 2, 8, 20, 50, 82, 126. I've cheated and called them magic already. And very large values in between those. Here's another magic case, and very large values in between. You already know the explanation of this. I gave this example after I did the toy model with the degenerate levels mixing. I then used that to calculate transition rates, and they were huge. And there you see, that's that effect you're looking at. Okay, that's the comment about that. So, the empirical magic numbers for nuclei near stability are 2, 8, 20, 28, 50, 82, 126. Sometimes 40 appears, sometimes 64. And even if we pretend we don't know what they stand for, what they represent, they provide a framework. And we'll see later where they come from when we look at the independent particle model. But for now, they tell you that something special is happening to the nucleus at those values. And so we will, this is now jumping ahead a little, we will think of nucleons as comprised of nucleons up to a magic number, and then those nucleons beyond that magic number we will think of as valence nucleons. So if I have a nucleus like lead-210, lead has 82 protons, lead-208 has 82 protons, 126 neutrons. Both of those are magic numbers. Okay, lead-210, then we can think of in some approximation as a magic proton, magic neutron plus 2 valence nucleons. And so we'll talk about valence nucleons often. And these numbers here, plus a couple of R42 values that we've already encountered, 2.0, 3.33, are the only things I'm going to ask you to actually memorize so that I don't have to keep saying them. Okay, these are spectra of nuclei that have 2 valence nucleons. So the case I just mentioned was lead-210. It has 82 protons, that's a magic number. 128 neutrons, that's 126 plus 2. And you see a spectrum where you have a ground state 0 plus, a big energy jump to a 2 plus, and then smaller energy jumps to higher spin states. Here's another example, 134 tellurium. It has 82 neutrons, that's magic. 52 protons, that's 50 plus 2, that's magic plus 2. Again, ground state 0 plus, big jump up to the 2 plus, and then closer line 4 and 6. Here's molybdenum 92, which is 50 neutrons. 42, remember I said 40 was sometimes a magic number. So here's 42 protons, 0 plus, big jump to a 2 plus, and then smaller jumps. Okay, these are characteristic spectra throughout the nuclear chart. I could have chosen other examples of nuclei with 2 valence nucleons. And we will need to understand these. And we will understand them tomorrow. Unless I get to it today, but I don't think I will. Okay. So those nuclei all have R42 less than 2. The 4 plus is closer to the 2 plus than the 2 is to the ground state. So R42 less than 2 is almost always an immediate signature of a nucleus very close to a doubly magic nucleus. Okay, now, if we start from a doubly magic nucleus, what happens as we increase the number of valence protons and neutrons? If we talk just about a few valence nucleons, you get something like this. This is tellurium-134. You probably can't read that in the back, but it was the one in the middle on the previous slide. This is tellurium-130. So tellurium-134 has 52 protons, 82 neutrons. 130 has 52 and 78, so that's 4 away from 82. And tellurium-120 has 52 and 68, which is 14 away from 82, or 18 above 50. And what you see is a very typical behavior. This sequence of energy levels where R42 is less than 2, you have a big jump and then smaller and smaller spacings, gradually evolves. The energies come down and they group differently. And by the time you get here, the grouping is 2 plus, and then at about twice that energy, a group of 3 levels. And then at about 3 times that energy, another group. And if you remember when we talked about the harmonic vibrator, I said that you could have a 1 phonon state, which was a 2 plus, and then at about twice that energy, there'd be a 4 plus. This is actually an example of that kind of nucleus. Okay, this drop in energy here is exactly the phenomenon we talked about with that toy model with n levels that mix, and the lowest state comes down lower, and the more levels you have that mix, the lower it gets. So here you have more and more valence nucleons, more and more initial states that you can make of a given angular momentum that can mix, and the states come lower and lower. So that's the emergence of collective behavior. And here are some practical examples of a bunch of them, ranging from nickel to barium, and all of them have, sorry, this is an example. It's an example of what's on the right here, where you have a 2 plus level and then a triplet at about twice the energy. And so you see barium-134 is a nice example, fluorine-122, cadmium-114, a bunch of others. So it's quite common in nuclei with roughly 6 to 10 nucleons outside a closed shell, maybe 15 particles or so. Okay? This is a somewhat famous example, cadmium-118, with that 1 phonon state, 2 phonon triplet, and what will turn out to be 3 phonons there. I won't go into detail on this. Okay, now what happens if you add more valence nucleons? If you add more valence nucleons, the spectra begin to look like this. This is an entirely different pattern. When we had 2 valence nucleons, you had a ground state, a big jump to a 2 plus, and a smaller jump to the 4 plus. when we had a few valence nucleons, a ground state, a 2+, and about an equal jump to the 4+. That's our 4,202. Here you see the energy spacings are expanding. You have a low line 2+, a bigger jump to the 4, and so on. And the R42 values for these nuclei are very close to 3.33. And so, although we haven't discussed the rotor in any detail, you can clearly see from this that this is the emergence of deformed nuclei. Okay, and they require lots of valence nucleons. So if you take this example, for example, strontium-160 has 66 protons. That's 16 valence protons beyond 50. And it has 94 neutrons. That's 12 neutrons beyond 82, so that's 28 valence particles. Okay. Nuclear radii are another measure of structure. And I won't talk about these very much, but this just gives an example of the difference in radii from one nucleus to the next, or relative to a magic number. And you see the typical trend is just a linearly increasing pattern. As you add nucleons, the nuclei get bigger. But then in some places you see big jumps. And that's when deformation sets in. Okay, because if you have a nucleus shaped like this compared to this, the root mean square radius will be bigger. Okay, so back here, I gave some illustrations of nuclei that look like, that have R42 close to 3.33, and I called them deformed nuclei. Now I want to look a little more detail about what a deformed level scheme of a deformed nucleus looks like. So this is erbium-164, which is completely typical. And you'll see this figure later when I discuss the models for deformed nuclei in greater detail. But for now, just a few things. You have a ground state, okay? And then you have a sequence of rotational levels. These are levels where the nucleus is rotating faster and faster. And the energy levels follow this formula, J times J plus 1. And that's this sequence of levels. Okay? And we'll come back to this. Okay. And then you have levels up here, which we don't know the structure of at this point in time. We will discuss them in quite a bit of detail. For the exercises this afternoon, I want to give you, though, one name. This sequence of states that starts with 2+ and then has 3, 4, 5, 6, and so on is called a gamma vibration. And it has a very specific kind of geometrical structure. So if this is a deformed nucleus, okay, axially symmetric, gamma vibration is an oscillation that looks like this, where it loses axial asymmetry on a dynamic scale. And that's called a gamma vibration for reasons that will be clear later. The only reason I make the point of mentioning this, because it's out of sequence, is that one of the exercises will ask you to look at the first gamma vibrational levels in a certain nucleus and to do something with it. Okay, so just remember that. Okay, that's why it's in red. And then on top of each of these states, this 0+ state and this 2+ state, oh, somehow something got covered there. Anyway, there are rotational bands built on these. So the structure of a deformed nucleus is you have some state, and the nucleus can rotate, and then you can excite that nucleus to some other state, either some oscillation or by exciting two particles to a higher orbit or whatever, and then built on that state, the nucleus can rotate again. And so every state, every intrinsic state where you start off with a given basic structure, the nucleus can then rotate. And so you get a series of so-called rotational bands, in each of which the energy levels follow this formula approximately. Okay, so this is a summary of what we've seen so far. Doubly magic nuclei with 2 valence nucleons have a spectrum like this. R42 is less than 2. Vibrator nuclei, you have a spectrum of 0, 2, 4 with 2 to 1 spacing. You'll see this later, and I'll talk about the rest of this. But for now, just notice the 2 to 1 ratio. Deformed rotational nuclei, sequence like that. Okay? Now, so far, we've looked at individual nuclei. This is a summary of the data for the entire nuclear chart. And it shows two things. Over here, it shows R42, color-coded so that blue is 3.33 and brown is less than 2. Okay, and so what you see are, you see the magic numbers very clearly at 50, 82, 50, 82 there, 126 here. And then as you go in the regions in between the magic numbers, you go from R42s of less than 2 to values near 3.33. It's a very clear and beautiful behavior. Over here I showed the energy of the first 2+ state. And if you remember, one of the characteristics of the first 2+ state is, thinking again in terms of this toy model, the more valence nucleons I have, the more states I can make that mix, and the lower one will be lowered more and more. So lower 2+ states also mean deformed collective nuclei. Here the color coding is that high 2+ states, around 1400 kilovolts are brown. Again, you see the magic numbers. And in the middle, you see these low values. Okay. There's a difference between 2+ energies and R42. 2+ energies, as you'll see soon, soon probably means tomorrow, they depend on the mass region. Whereas R42 is almost the only observable whose absolute value directly tells you something about structure. One other comment, well, that just shows the magic numbers. If you remember, I said on the very first slide that one of the amazing things about nuclei is the regular and simple patterns that they show. I think this is one of the most dramatic examples. And I think it's one of the real beauties of nuclear systematics. And whether these persist as you go far off stability is going to be one of the big questions for the future. It's already a big question. And in fact, in light nuclei, we've already seen cases where the magic numbers change. I want to just take a step back, and we should all be amazed for a minute. Take a nucleus with a couple hundred particles. If you just add up the volume of all the nucleons, it's about 60% of the total volume of the nucleus. And these particles do about 10 to the 21 orbits per second. So what would you imagine if you had 200 particles occupying 60%, 200 marbles occupying 60% of a balloon, making a 1,000 billion orbits per second? You would kind of expect complete chaos, right? I mean, even if I just took the 35 of us and we ran around this room 1,000 billion times a second, it would be a mess. We'd all be on the floor dead in a few picoseconds. Anyway, but that doesn't happen. Instead of this chaos, the behavior is very regular, reflecting some ordered, coherent motion, and this should astonish you. And how can this happen is one of the challenges of understanding nuclear structure. Yes?
What do you mean by this orbiting?
So what we will find out when we study the independent particle model is that one picture of these nucleons is that they go in orbits around the nuclear center. Okay?
It's not just like a probability cloud around it?
If you want to think of it that way, yes, but you can also think of it in terms of orbiting with a certain angular momentum.
Okay.
Okay? Okay. Caveat. These magic numbers, which were the cherished, beloved benchmarks of structure for 50 years after the shell model was invented in 1948, have suddenly, not suddenly, but over the last 15 years, it's been found that as we study nuclei away from stability, the magic numbers can change. And this is one of the most important aspects of research with exotic nuclei. And this is just a little chart showing some new magic nuclei that don't occur at the traditional numbers. Here's 14 and 16. And some nuclei you might expect to be magic that aren't. Here's a 20 neutrons, and it's not magic. And so the magic numbers evolve. They're not the rigid, robust creatures that we thought they were. There are reasons for that. Proton-neutron interaction is important, weak binding, but just for now, realize that they can evolve. And here's a plot that shows that. This is the magnesium-calcium region. It shows the energy of the first 2+ level against neutron number. And what do you expect? You expect high values near n equals 20 and 28, which are 2 magic numbers. And you certainly get them for calcium. And you get them for, at n equals 20, you get them for argon, silicon, and sulfur. But look at magnesium. N equals 20 for magnesium is a low number. And in fact, before these 2 nuclei were known, it was the lowest. And so magnesium with 20 neutrons is clearly not magic. In fact, it's collective. And this was somewhat of a shock when it was discovered. And so it has to do with changes in the energies of single particles orbiting the nucleus as a function of neutron and proton number. Okay, and over here, silicon, sulfur, they show very small peaks relative to calcium. So n equals 20 is not magic for magnesium. N equals 28 is not magic, at least for silicon and sulfur. And this is one of the most important areas for research. And when we went around the room and you told me what you were doing, a couple of you, at least one that I remember, said they were doing their work on the magnesium island of inversion. That refers to this effect there. Okay, this is a semi-quote from Ben Mottleson. It's not exactly a quote. He told me when we were sitting at lunch together. So it's as close to a quote as I can get. Have you all heard of Ben Mottleson? Born Mottleson? Okay. They're famous for having developed the collective model. And so you might not expect them to be thinking too much about individual nucleons. But he said this: shell gaps, magic numbers, and shell structure are not mere details, but are fundamental to our understanding of one of those basic features of nuclei, independent particle motion. If we don't understand the basic quantum levels of nucleons in the nucleus, we don't understand nuclei. Moreover, perhaps counterintuitively, the emergence of nuclear collectivity itself depends on independent particle motion and the pellicles. Okay, so we need to understand the magic numbers and these nucleonic orbits. Oops, wrong way. Okay. So, for that reason, I'm going to talk about the independent particle model now. It's a model about what the nucleons are doing and how we can understand the magic numbers. And I will do it in a very informal way. Pete, on Wednesday, is that your first lecture on Wednesday? Right. On Wednesday, we'll go through it in a proper way, okay? And hopefully between the two of them, you'll understand it. I keep clicking this thing. Okay, so how would we calculate the structure of nuclei? What we would like to do is take some nucleon-nucleon force, and here's a plot of it, roughly. It actually has other kind of dimensions to it, but it's short range, so it doesn't go out very far in radius. It's attractive. There's a repulsive inner core, which in some sense reflects the Pauli principle. And what you'd like to do is take A nucleons and put them in this potential and solve the Hamiltonian, which has kinetic energy and potential energy terms. Since it's three-dimensional, that gives you 3 times A degrees of freedom. And unfortunately, that's too complicated to deal with except for the lightest nuclei. There's been amazing progress on this side in the last 10 years. I mean, truly amazing with what theorists have been able to do. Maybe some of you were involved in that. But in general, it's too complicated for most nuclei. And so, we have to do something else. Now, nuclei are not like atoms. There's no central nucleus at the center of a nucleus. There's just stuff everywhere. But nevertheless, we make the approximation that if we take the interactions of all the nucleons together, they can create an effective potential or central force. Okay, so what we do is replace this nucleon-nucleon interaction by an average nuclear well in which all the nucleons live. And it looks something like this. The details are not so important. And the nucleons live in here, and they will have various energy levels, which we will look at in a minute. And we change this Hamiltonian from a many-body Hamiltonian into a one-body Hamiltonian, where we have the Hamiltonian of this particles in a potential, and then some residual interactions. And first what I'm going to talk about is this part, and then we'll add this, and this will probably be the first thing I'll do tomorrow. Now, the extreme approximation of using this one-body potential, I mean, it can't possibly be the full story. You can't take 200 nucleons all interacting in various complex ways and replace it by a box. Okay, so we'll see how far we can go with that, but we will need this in a very important way. But we can do a little bit without it. Okay, so there are three key ingredients. My problem is I can't see my arrows because it's dark here. So sometimes they hit the wrong one. Anyway, there are three key ingredients. One is interactions between nucleons. The second is quantum mechanics. Okay? We're basically putting the particles in a box. And let's just talk about it as an infinite box for now. That means the wave functions have to go to 0 at the edges of the box. Okay, so that's basically the fundamental origin of quantum effects. Namely, confinement limits you to only particles with certain wavelengths, certain energies. The wave functions have to go to 0 at this end and at this end. And so the lowest energy, the longest wavelength, would have a wave function that looks like this. The next lowest would have one extra node, it would look like that. And the next would have an extra node, and it would look like this. And so these are the only low-line states that a nucleon in this box can occupy. And since the energy goes as 1 over the wavelength, this would be the lowest energy, this would be next, and this would be next. So confinement, putting the particles in a box, is the origin of quantized energy levels. And notice that if I call n the number of nodes or the principal quantum number, the energy goes up with n because the wavelength is shorter. Okay? That's very simple. Just to show you how really simple it is, if you can derive the lowest energy just by, without even the Schrödinger equation, just using the de Broglie relation. So the de Broglie relation, just using this confinement idea, that n, some number n times the wavelength, has to equal the distance d. You use the de Broglie relation relating wavelength and momentum. Use E equals 1/2 mv squared, which is the same as p squared over 2m, or p equals square root of 2me. And the beta, the small component of the mixing amplitude, is 0.1, and beta squared is 1%. Here you have the same initial separation, but a large matrix element. And now this 200 kilovolt level moves 62 kilovolts. And the mixing amplitude, I mean, it's almost completely mixed, or at least it's very large mixing. There I have 500 kilovolts and 25 keV interaction. That's not so different than the first one, but I just wanted to kind of show you that things scale. And then the upper level moves a little over a kilovolt, and the mixing amplitude is quite small. So those, I actually wanted you to do by hand. Hand to me means actually with one of these things that you write with. Have you seen those? They're called pens. They don't have little buttons. Some of you couldn't resist using Excel, but anyway, I was hoping you'd do them by hand because you actually learned something by seeing the numbers fly by. In any case, I think you all got these in the end. Here are two degenerate levels with a 10 kilovolt mixing matrix element. And so the first level moves up 10 and one goes down 10, and the mixing is complete. It's as mixed as they can get. And here, same two initial levels, 100 kilovolt interaction. Now the one moves up 100 and one moves down 100, the same mixing. What I wanted you to notice here, in addition to the energies, here I say D and E, what do you notice about the wave functions? Notice the wave functions don't change. Now, in every other case, if you have non-degenerate levels, and you mix them and you change the interaction strength by an order of magnitude, the wave functions will change tremendously. But not for the case of degenerate levels. That will turn out to be important in the third week when we discuss, for example, the IBA model and the idea of symmetries. And then here, 5 degenerate levels, all at 1,000 kilovolts, all mixing with each other with interactions of 100 kilovolts. So one level goes down to 600, 4 go up to 1,100, and all the wave functions are constant. What does that mean? Oh, I asked for the wave function of the lowest state. It's just all amplitudes with 1 over the square root of 5. All amplitudes equal. Okay, that was pretty simple, but since it was the first exercise, it took a while to get into things. Now here, I asked you to diagonalize. Oh, by the way, see the word negative. Some of you missed it because it was in red. I should have said here negative as well. So sorry about that. Anyway, here I gave you some levels which are not degenerate and some sort of random matrix elements which are fairly large. And I asked you to diagonalize it with Mathematica, and I think in the end just about everybody got connected with Mathematica. Maybe 1 or 2 of you still have problems. Here's the input, here's the output, and there's several things to notice. Remember, the input energies were 500, 600, 700, 800, 900. Let's start here. The 900 moves up, the 800 moves up, the 700 moves up, the 600 moves up, the 500 moves way down. Okay, so one level again is lowered substantially, the others are raised. And look at the wave functions. This is the wave function of the lowest state. You'll notice, first of all, that the signs of all the amplitudes are the same. And you notice they range over a factor of about 4, from 0.8 to 3.1. Look at the other ones. For example, this one. The amplitudes range over 2 orders of magnitude, from 1 to 169, and you have a mixture of states. So it's a feature of the degenerate case that one state goes down and is lowered, and all the amplitudes are in phase and are equal, the others are all raised. This is not a degenerate case, and it's not all equal matrix elements, it's more realistic, okay? But you still get the same basic qualitative feature. One level is lowered, the others are raised, and the lowered one has a coherent wave function with all the amplitudes in phase. Okay? I asked you to compare the independent particle model predictions for the first 4 states with antimony 133 and terbium 169. Now, if you remember the comments, some of you were puzzled by this because the antimony didn't work exactly. You got the rights, 3 of the 4 states had spins and parities that were consistent with experiment, but the order wasn't right. And if you remember when I showed you the independent particle model diagram of levels with the magic numbers, I said, don't believe these. I mean, don't take them as coming from the mountaintop. They're a snapshot for a given mass, and they will change with mass. As the radius of the nucleus changes, high and low angular momentum orbits are affected differently. Lots of things can happen. Coulomb effects and so on. So these are snapshots for a given mass region. And the one I showed you might have been calculated, I don't remember where I got it, it might have been calculated for some mass 50 or something instead of mass 133. And so the order of these levels can change. Okay, they generally won't go from one major shell to another, but within a shell you can get shifts. So don't be too shocked if you see that. So some of you actually used a different diagram, which you liked better, and which actually worked better. It was probably more tuned to that mass region. Okay, for 169 YB, this was, in a sense, a trick question. The answers you would get just using the independent particle model by taking the 70 protons here and just assuming they all pair to 0 because of the residual interaction. And this has 99 neutrons, taking 98 of them and pairing them off. And then you have one last neutron, and looking in the shell model diagram and seeing what orbit it falls into and then putting it up into successive orbits. You get this, you could get slightly different versions depending on how you do it. They have nothing to do with the data. The data doesn't look like that at all. And so some of you realize that this would probably happen since this is mid-shell in protons and mid-shell of neutrons, and so you don't expect this model to work, and I want you to see that it didn't work. And in the third week, we'll discuss a model called the Nielsen model, and you'll see how simple it is to understand something like that. Okay. Now I asked you to look up the ERAS levels in NMDC for these nuclei and to comment on their structure. I specifically asked you to look only at the ERAS levels because with the models we discussed yesterday, that's all we talked about. Some of you knew about other things and tried to fold that in, which is fine, but I wanted you to sort of take you step by step. So for cadmium-112, if you look at the 4:2 energy ratio, it's about 2.3. And so most of you correctly said, well, it's close to a vibrator, but not quite. The vibrator, if you remember, has 2.0. It turns out experimentally that nearly all nuclei that we usually associate with vibrational structure don't have R42s of 2.0, but have R42s of typically 2.2 to 2.3. This is about as good a vibrational nucleus as you can get. There is even currently dispute in the literature about whether it really is or not, but it looks pretty good if you look at all the data, I think. That's my opinion. Okay. 164 dysprosium had an R42 value of about 3.29 or something, and some of you said it's a perfect rotor. Well, it's a good rotor. It's not a perfect rotor, because perfect would be 3.33, and we will see where those small differences can be important later. 152 samarium has an R42 value of 3.01, and so you said it's transitional. Most of you got that right, which is good. 190 osmium I put in here. This again is kind of a trick question. It has an R42 value of 2.87. I can't remember. Anyway, and you said it was transitional. You will see today that there's more to it than that, and you have to look at non-ERAS levels to see that. 238 uranium was simple. For these two nuclei, I think the 4:2 ratio in one of them is not even known, and so I put the comment here. This actually wasn't in the question itself, but I said it verbally. R42, if you only have the ERAS levels, R42 is very useful. But in some cases, it's better to look at E2 plus alone. And if you made a plot of E2 plus for silicon and for magnesium as a function of neutron number, you saw a big jump for silicon at n equals 20. And big jumps in E2 plus are symptomatic of magic nuclei. And no jump at all in magnesium. And so what I wanted you to see here was that the magic numbers can change. Okie dokie. All right, so here, now I've changed the question from the one you saw yesterday because we were running out of time, and so I said to simplify it. The question you saw yesterday asked you to do a look at the decay in erbium-168 for all the gamma band states. But then I said just do it for the 2 plus gamma and also ignore uncertainties. We will come back to this today, and you will be tortured by having to do some more work on that. And I asked you to normalize this transition to 100 and make a table. And the table is coming up. Here is the table. So the 2 to 2 is normalized to 100. The 2 to 0 is 56.2. The 2 to 4 is 7.3. And I think in the end, more or less, all of you got that. There were some steps along the way where you got different numbers, like 2042 or something else, but in the end, there was just numerical mistakes. The key here was just getting a little bit familiar with this e to the 5th factor. Okay, now, you'll notice this table sort of cuts off here and is kind of short. In one of the exercises today, I'm going to ask you to fill this out for the 3 plus, the 4 plus, the 5 plus, and the 6 plus. And for the 3 plus and 5 plus, to come up with these uncertainties as well. Calculating the uncertainties is a little bit of a pain in the neck, but it's very important for both experimentalists and theorists. If you're going to compare with the data, you've got to know how accurate the data are. And there will be another column out here that I'll ask you to fill in. We'll discuss that topic today. Okay, now I
So-
asked you which theory is
Can
better.
we just a question about the fifth exercise? When we have a ratio and we normalize to something, how do we calculate the error?
Okay, good question. So, there are two different ways.
Oh,
If you look at the intensity of this in the nuclear data sheets, it has an uncertainty of 2%.
yeah, it also has a certain, but
Yeah, so you could put 2% there, 2 on the last digit, and put the uncertainties for each of these. What most people do is to
fix this.
fix this at 100 and combine those two errors into here and into here, just in quadrature.
Uh-huh.
Okay,
And
it's a
which
little,
one is right?
huh?
Which one is right?
I don't think either is right, but if you talk about normalizing one to 100, it's nice to think of it as having that value. I don't think there's a
We
right.
fix this and
I
get
don't
the
think
error.
there's a right and wrong. This is the way I do it. It's the way I think most people do it, but I've seen the other as well. Okay? Okay, so I asked you which theory is better. Now, I'm not sure all of you got to this. Who actually got to do this? Raise your hands. Okay. Who didn't get to do it? Who didn't raise their hand for either answer? Okay. You guys study some rules, don't you? Okay, so let's actually do this here. So, which theory is better? Theory 1 or theory 2? And I'm not going to embarrass you. You can all close your eyes and just raise your hands. Who thinks theory 1 is better? Who thinks theory 2 is better? Who doesn't think? I didn't see every hand up. I want to see all the hands up. Who thinks theory 1 is better? Who thinks theory 2 is better?
I don't think the other time.
I noticed your hand wasn't up. Okay. All right, why do you think theory 2 is better? Yeah? No, wait a minute. You did it yesterday. So
Yeah.
the people who did it, I don't want to answer.
Okay.
Why do you think theory 2 is better?
Because it matches with the experimental data pretty well in these structures.
Okay. All right. Let's look at chi-squared. So let's calculate the difference between the experimental and the theoretical values divided by the experimental error. And what do you get? You get that chi-squared for theory 1 is 2 times 10 to the 4th, and chi-squared for theory 2 is 10 to the 6th. Now, let's vote again. Who thinks theory 1 is better? Who thinks theory 2 is better? Who heard me say that theory 2 is better yesterday? Okay. So why? What's going on? What's the message here? There are actually a couple of messages. This is a very important point because all of you, whether you're theorists or experimentalists, are going to be comparing data with theory, or you're going to be doing theory so exotic that there's no data ever possible on it. But let's hope that you're here because you're going to do something practical. So you'll notice here that this experimental energy is accurate to 1 electron volt. And so is this. And these are accurate to 2 kilovolts. Now, first of all, that's not impossible. There are experimental techniques that do this. It's fairly straightforward, although uncommon, to measure gamma ray energies to an electron volt. And perhaps these states were not seen by gamma ray spectroscopy, but by particle spectroscopy. So you could easily get this. What you have here in theory 2, by the way, theory 2 is better. What you have is nearly perfect agreement, but 1 kilovolt off. But when you take into account that this is 1 electron volt uncertainty, the chi-squared is just absolutely dominated by that. That's a factor of 1,000, which when you square it is 10 to the 6th. Okay? What's missing is the idea of theoretical uncertainties. You need to, whenever you make a comparison of experiment and theory, you need to fold in the idea of how accurate you expect the theory to be. Now, we could get into a long discussion of how you know how accurate theories can be, but we won't. But in any case, somehow you have to estimate, or take into account somehow what you expect for the theory. Okay? And if the theory if you say the theory should be accurate, let's say to 10 kilovolts, then using 1 electron volt here is just going to misguide you completely. So here I do an example where I take 10 kilovolts for all the levels, okay, and I write the errors like this. And then I get new chi-squareds, 800 and 0.01. And that much better reflects the actual quality of these two calculations. So the message here is take theoretical uncertainties into account. And you can fight for days and weeks about what value to put in here, but at some level you have to put in something. And if you don't, you'll make wrong conclusions. And so one message here is don't let super precise data bias your model testing. That's not a message not to measure things precisely. Okay, it's great to measure things precisely, but don't let an accidentally precise value like this completely dominate the comparisons. Okay? All right. So this example had to do with what you do when faced with precise data and the idea of introducing theoretical uncertainties. And for this example, I'm just putting in 10 kilovolts for everything. Now, here's another example. Which theory is the worst? So who thinks theory 1 is the worst? Who thinks theory 2 is the worst? Who thinks theory 3 is the worst? Who knows that I think theory 1 is the worst? Who's not being honest? Okay. Why do you think theory 1 is the worst? They're all the same chi-squared. Each one misses a level by 100 kilovolts. No, you did them. Somebody who didn't, did you do them yesterday? Okay.
I would just guess, one, because you want your theory to hit the lower lying excited states more precisely. Because being off by 100 there is like a 100% error, whereas being off by 100 when your value is 1300 is only like a 10% error.
Who agrees with that?
Sweet.
Everybody disagrees with that? Who agrees with that? Who disagrees with it? So all the other hands should go up. Okay, why do you disagree?
Well, I think I won't be honest because we discussed all
Okay,
this.
then don't say anything.
Yeah. I mean, we discussed.
Yeah, okay, but I want people who haven't discussed
Yeah,
it.
sure.
Did we discuss?
Well,
Did we discuss?
No.
Okay.
I think Justin made a good point about.
Which one is Justin? I haven't memorized all the names yet.
But in this case, we've been studying the E42 value, and that is what we use to characterize the rotational vibrational mode. So having the 4 state be off by 100 kilovolts is going to mischaracterize.
Okay, you're both right. I don't think, so to get this wrong it really means the entire theory is getting the nucleus wrong. It's saying it's something like a vibrator. It's not exactly a proportionality to the energy. It's not the fact that, whoops. It's not the fact that these are 4 times. How long was that stuff up there? Was it up there all the time?
No, just
Okay. Okay. It's not just the fact that these energies are 4 times higher. It's that these are, you can see this is a rotational nucleus. These are simply rotational excitation energies, and a theory should be able to get those to within a few kilovolts. And to miss the structure completely means the theory is just absolutely wrong. These two get that level perfectly. One is off by 1 and one's off by 100 here. I'm not going to go into which one of these two is better. I personally think this one is, but if not, we don't need to discuss that. Okay, so here you have what I just said. Theory 1 misses the structure completely. And the message here is you need to put some physics insight into evaluating knowledge. You can't just go blindly and look at chi-squareds. Well, here it wouldn't help. Or just say, well, they're all equal. And there's another message. So this is what I just said. The theory should get the ERAS energies to within a few kilovolts. It's really easy. Lots of models will give you that. And you're generally happy with these vibrational energies if you're within about 100 kilovolts. If you put those theoretical uncertainties in, you get 1001. Okay? There's a message here which may not be, I mean, it's the important message is that theoretical uncertainties are observable dependent. So in the previous slide, we took 10 kilovolts flat out for all the theoretical uncertainties. Here, we have one theoretical uncertainty for the ERAS levels namely 3 kilovolts, and another for here, 100. So the theoretical uncertainties depend on what observable you're looking at. Now, it's not so easy to have a rigorous formula for how to do this. A lot is based on experience and so on, but it's something you always need to take into account. Okay, so that is good. That's what I wanted to do on that.